is a talk about Riemannian geometry. So our manifolds are always complete, connected, Riemannian, with their standard names like N for manifold or S for surface. And if we have such a manifold, we have the Laplace operator. And the Laplace operator, under the assumptions which I wrote down, for a complete Riemannian connected, well, for a complete connected Riemannian manifold, it's essentially self-adjoint on this. If you take as domain the space of smooth and complexly supported functions. So it has the natural extension as a self-adjoint operator, and that operator has a spectrum. That spectrum is called the spectrum of the manifold, because the Laplace operator, of course, is a natural operator. And if you have the spectrum, so let's say sigma of M, the spectrum of M, so M is now such a manifold, then you have lambda 0 of M, the bottom. So the infimum and you can get it as you can get it as the infimum overall. You take all functions phi, which are C infinity, have complex support, and are non-zero, and you take the Weyl equation of this function, which is equal to the integral of the gradient over the integral of the function squared. Okay, so that's the bottom of the spectrum. And this is an important number for compact manifolds or finite volume at 0. For the hyperbolic plane, it's 1/4. That's the famous 1/4 occurring in many results. And there's another number which is infinity in the case of compact manifolds. It's called the essential spectrum. Yeah, the bottom of the essential spectrum. So that's the bottom of the essential spectrum. Of M. So the essential spectrum consists of all numbers lambda, so that the Laplacian minus that lambda is not a Fredholm operator. That's the definition. But here in our situation, there's a geometric description, which is the following. And this is equal to the supremum over all compact subsets in M. So that's compact. And then we take lambda 0 of n minus k. Okay, this is not a complete manifold, but we take the same kind of definition as here. And that's the lambda 0 of m minus k. And you take the supremum, which means if you take bigger and bigger k's in the limit, you will get this number. It's something which is associated to the structure of the manifold at infinity. So that's the infimum of the essential spectrum. And so for lambda less than lambda s of m, Laplace operator minus lambda is a Fredholm operator. And so eigenspaces below the bottom of the essential spectrum are finite dimensional. The eigenvalues are isolated, and you can count them. The operator is, of course, non-zero, non-negative. So for lambda less than 0, of course, it's trivial space. So we have this in general finite interval, but for compact manifolds, it's in lambda essential from M is, as you can see from that result already, it's in infinity. So below this lambda essential from M, we will count eigenvalues. And for compact manifolds, of course, we can count them up to infinity. Okay. And so what we are discussing is we have two such manifolds. And we look at coverings. And we look not any kind of coverings, we look at Riemannian coverings. Which means that locally, we are talking about the covering. Locally, it's isometric, and so then, of course, if you have a function phi on M, you can pull it back, and you can take the Laplacian. The Laplacian is always denoted delta independent of the manifold, if there's no kind of danger. Then we have this relation, which means if delta phi is equal to lambda phi, if we have such an eigenfunction, then p star of lambda phi, of course, is lambda p star phi. So then eigenfunctions go to eigenfunctions. Pull back, you get eigenfunctions for the lifted metric on M prime. Which means if we are below this number, we have finite dimensional eigenspaces. By the way, this number, I should say that. Usually, I assume finite, not always, but for the question I will ask now, I only want finite degree. So when you have an L2 eigenfunction, the pullback will be L2. It will also be an eigenfunction. So this L2 spectrum of M is part of the L2 spectrum of M prime. The question which I ask is there anything new for M prime? And in general, one would expect that. Let me start with just as a reminder and also as something to warm up with a node result of Randolph. So Randolph says if it is let S be closed hyperbolic surface, hyperbolic means Riemannian with curvature equal to -1, right? Just to be definite. So then given n, n in n, the natural number n, there exists a covering a finite so when I write something like this, I mean a finite Riemannian covering. So finite, I added this, such that S prime has at least n eigenvalues less than 1/4. So remember, for the hyperbolic plane, curvature -1, this normalization, the bottom of the essential spectrum is 1/4, and that's one of the reasons that this number 1/4 occurs here. And
well, you say it's finite covering. So I consider finite hyperbolic plane with finite cover divided by finite group. I'm confused. It's one before you have on the bottom.
S is a closed hyperbolic surface.
Closed.
Closed.
Yeah.
And I'm saying that you are giving me any number n, then there exists a finite covering. So it also has a hyperbolic metric. You just lift it. And this, with respect to this lifted metric, this new surface S prime has at least n eigenvalues below 1 over 4. Is it clear what I mean? Did I answer your question?
Well, there is eigenvalue less than 1 over 4. Okay.
Yeah. So let me just give, maybe then it will become more clear. Let me just give an elementary. So he used it using.
But there is no compact surfaces with exactly 1 over 4. They're all distant 1 over 4. It never 1 over 4. I'm confused.
I didn't understand. Or there are no?
1 over 4 is what we have upstairs in the universal covering. All compact things have small eigenvalue. All have a small eigenvalue. You never have 1 over 4. I'm confused.
I'm saying it has at least n eigenvalues. By the way, not all closed hyperbolic surfaces.
There are n eigenvalues. I'm sorry, n eigenvalues.
Yes, okay. Yes. Oh, okay. Yeah.
Okay.
Let me give. So he used the proof of Randall. He used the Selberg-Trace formula to show this. I guess let me just give a very elementary argument. Take such a surface S. So you can think of it as, say, for example, could be non-orientable. That doesn't matter. S has a simple closed curve on it, smooth, embedded, so an embedded circle, which does not separate S. Oh, yeah, okay. Actually, it's not important that it is hyperbolic, by the way. So just notice that I could have stated it a bit more generally. So there's such a surface, and what I'm saying is it has a closed curve on it. So when you cut the surface along that closed curve, it is still connected. So you do that, and topologically you have something like this. So the circle you cut it open, and you have there's two boundary components now. I'll draw one to the right, one to the left, one to the right. And there may be some topology inside there. Yeah, there will be some topology in general. So you could have done, actually, you could have done this also with a torus. What you do now is the following. Okay, you take many such copies of your surface cut open. Now you consider the following function. You take a little neighborhood of that curve, and you let the function be zero. You let the function grow from 0 to 1 on that part. Then you have it equal to 1 on all of those. You choose a small neighborhood here of the boundary circle, and you have fall down to 0. So what is the Rayleigh quotient of that function? Well, it is equal to 1 on a very large part. So the denominator is as big as you like. But the numerator is only to the numerator, the only contributions are where the gradient is non-zero, and that's on this small part and on this small part. So the numerator has a fixed constant. The denominator you can, the denominator you can make as large as you please, but by choosing sufficiently many copies. So you have a function which has a Rayleigh quotient less than epsilon if you have an epsilon given. 1/4, but you could take any small epsilon. Okay, so you have one such function on this part. Now you want maybe n functions, which are perpendicular in L2. So you take this, you glue, I forgot to say, you glue these in-between pieces all together along these closed curves. They fit together smoothly, the Riemannian matrix, because this curve corresponds to this curve. This curve corresponds to this curve, and so on. So it fits smoothly to a Riemannian manifold with boundary. Boundary is, again, this circle. And then, well, you have one such function, then you take n copies of this big thing and glue them together again. So you have a very, very long line of such surfaces. And then you take the two outer curves and glue them together. Then we have a smooth Riemannian manifold surface. And it has n functions which are L2 orthogonal because their supports are disjoint. The Rayleigh quotients are less than epsilon. So this function has certainly n different eigenvalues below below epsilon. And it covers the original surface because you just project this on the surface as you started with, yeah. So you have the cyclic covering of a surface, and this cyclic covering has at least n eigenvalues below epsilon. Did it become clear?
A priori, they may be all equal.
Pardon?
That all eigenvalues may be equal. We have eigenspace of this dimension, but eigenvalues may happen to be equal.
I don't have an eigenspace. I don't know what the eigenvalues are, but you are right. It could be I always count eigenvalues with multiplicity.
You didn't say with multiplicity.
If
I see what you wrote, I wrote eigenvalues.
Yeah. That's.
I'm not certain your spelling, but I think. Of course, you can perturb it a little bit. You can perturb it and make it positive.
Multiplicity.
With multiplicity. Okay. This was my. Okay. Then of course. Okay.
Thank you.
So why did you 1/4? Because you can get any epsilon.
Yeah, that's what as far as I know what Randall proved.
Okay.
Yeah, so we get a somewhat stronger statement, but this very elementary argument.
And your cover is always cyclic, right?
This cover is cyclic, yeah. But you can do this, of course, in many ways. If you look at it, you can cut it on different places and stick together these different pieces. You get tree-like covers. So you can vary this construction.
It's anyway, there is no trivial. Anyway, I have cyclic covering, that's it. You don't need all this geometry. For any cyclic covering, you do it. If you have manifold admits infinite cyclic covering, you have it.
Yeah, you can probably also.
Why to do this geometry? You just take any slow growing function. That's it. It's obvious.
Yeah. That's.
You don't need all this geometry. Just about H1.
You want to do it without geometry. You don't want to take any kind of computation.
No. I was just saying anytime we have cyclic covering convention, so this obvious function, just the distance of any point, so to speak.
Yeah. That's true. Yeah.
It's obvious.
And that's what, so to speak, the point is.
No, but when I say 1/4, whatever, it was confusing because some obvious remark about cyclic groups here.
I'm not sure that, yeah, so okay.
It's true for circle. Therefore, it's true for anything which goes to the circle. Take pull back from the circle. It's an invariant under this kind of maps.
Yeah. So I'm not sure that I understand. I mean, what you say, but yeah. I guess
actually, we were true whenever you have an amenable homomorphism from the group.
So this
define it as
generates
groups.
Yeah. Okay, so
I think the point is that we get these small eigenvalues in a more general situation. But I guess that you want to do something more specific now.
Just to show you an elementary argument how to
Yes.
to achieve this. It's not a big deal.
Yes.
So in general, you may expect after this that maybe in general one should expect that in these covers you have you have the multiplicity of the eigenvalues grows or you have more eigenvalues. But there's the following result due to height and Meggy. So that's in the annals of 23, annals of math. So let S be the finite area hyperbolic surface and epsilon positive. Then asymptotically almost surely I have to maybe explain what that means. The Laplacian also almost surely in the degree n of the covering so as n goes to infinity, the Laplacian S prime to S. So you have such a covering. So with covering degree, the covering degree I always denote by absolute value. The covering degree. So almost surely in the degree n of the covering, there's no new eigenvalue on S prime in the interval 0, 1 over 4 minus epsilon. Let's make it open. So below 1 over 4 minus epsilon. No new eigenvalue, including multiplicity again. So what does it mean asymptotically almost surely? So you look at all coverings of degree n, and then the proportion of those, that's what you mean by this asymptotics. The proportion of those among all of those goes to 0 as n goes to infinity. So I find this kind of...
Okay, can you repeat again? Can you repeat it? Exactly, what is the statement?
So you start with a finite, sorry.
Say compact is okay, right? It's important to find area, compact is...
Non-compact, finite area, non-compact hyperbolic surface.
Non-compact, it's non-compact, okay.
Yeah.
Please slide the blackboard down tiny bit because it's in the shadow, so we don't see the top.
Yeah.
I think that's right. Yeah, thank you so much.
It's non-compact. Okay.
Yeah. So you have a non-compact. So the point actually is in this, for the non-compact, is the fundamental group is free. That's an important part of the discussion in that paper. And you are given any epsilon, then for that given setup, you look at coverings of degree n, and then look at the proportion of those where you have new eigenvalues, including multiplicity, and the proportion of those goes to 0 as n goes to infinity.
Wait. Now, because it's non-compact, it's spectrum. Spectral points are actually discrete and discrete part of the spectrum.
So we are talking about eigenvalues below 1/4 minus epsilon. That part is discrete.
About the discrete part of the spectrum. Okay.
So the essential spectrum of a finite area hyperbolic surface is one. The bottom is 1/4 if it is non-compact.
Yeah.
So we are below that. So you can talk about eigenvalues and their multiplicities, and that's all well defined below that. So I mean, this argument which I presented is also works for. I mean, it's just a very elementary argument, and it works for finite area hyperbolic surfaces as well. I mean, that's not a problem. And in many other cases, by the way, it's okay. So yeah, so that's this result which I found very surprising, I must say. And so they also have results in the compact case, but they are too complicated to state here. So and I didn't really study them as well as I studied this part. So our research. I mean, I should have said what I'm writing now down is joint work.
May I ask you, if it's an arithmetic case and you take its congruence coverings, would it be satisfied or not?
It's
in the arithmetic case, take arithmetic surface, take congruence covering what P or covering. Spectrum doesn't go to 0, you know.
So the arithmeticity, I'm not sure. I don't see any kind of way of bringing that into the game somehow.
No, because for this case, you do know the spectrum doesn't go to 0, and you know by Selbig conjecture, you know what happens to the spectrum, right?
The Selbig spectrum I just didn't completely understand. So here, there's nothing about arithmetic surfaces, but of course they are probably only a small proportion of all coverings, yeah?
Yeah, exactly. That's what I'm asking. Or if they in the spirit of this covering, or they're completely different, just to how they look like this interesting coverings. Are they the words which kind of in spirit of the congruence coverings already quite different? Most likely they must look like that, yeah. So you still
I think they don't. I mean, I think there's probably, as far as I understand the proof, there's no way of bringing in arithmeticity in any way, if that is your remark. Because what they do in their proof, by cutting the surface in pieces and taking resolvents on these different pieces and patching them together and so on, they created so in the original surface and correspondingly in the cover, they created a situation where they can apply a matrix random theory. And in this matrix random theory, I think everything like arithmeticity or so is lost, I guess. So there's a result in arithmetic in random matrix theory, which is crucial in this proof, and this. So that says something about the about this probability. So you get the probabilities from that result in matrix, in random matrix theory. And I don't think that arithmeticity can be brought in there in any way. But I'm not really an expert, but I don't think it's possible. Is that what you mean by your remark, Misha?
Yeah, I think so. Mhm.
So what I wanted, yeah. So this joint work with Shugata Mondal. So far there's no joint work, but so we were kind of motivated by this result. And so what
One sec, I must apologize. I left my charger in my office. I have to go to my office, so I have interruption for 10 minutes.
Yeah, okay.
Okay, excuse me.
Sure. I mean, I could also go away for 10 minutes, but
No, yeah, so I think we go on.
So what we looked at is the following situation. So you have lambda. So you have lambda eigenfunction. So delta phi is equal to lambda phi. And then when you have an eigenfunction, people talk about the nodal domains. Those are the components of connected components of, if you want, of the set where phi is non-zero. And then in dimension 2, they're called nodal lines, but in higher dimension, nodal set. This phi is equal to 0. Sometimes also denoted C5, for example. And so you probably remember this discussion. There's something like Courant's lemma or whatever. There's actually two of them. If you have on a closed manifold, if you have an eigenfunction for the first non-zero eigenvalue, then it has at most two nodal domains. The construction behind that, or the idea behind that, is the following: if you have a nodal domain, you could have, of course, you could have topologies. So then, on the boundary of this nodal domain, the function vanishes. So if this nodal domain is not too bad, you have a solution of the Dirichlet problem on the nodal domain. If you have another nodal domain, that's a similar thing. You also have this, maybe it's negative here. But if you have three such nodal domains, what you can do is if you look at this Rayleigh quotient, if you make the function 0 on one on all other nodal domains, but for one, you have still a function with the same kind of Rayleigh quotient because you have an eigenfunction. So from the nodal domains, you can create different L2 perpendicular functions with Rayleigh quotient equal to lambda, if we have a lambda eigenfunction. And so if you have many nodal domains, you get a corresponding subspace of functions which are perpendicular to each other, have Rayleigh quotient lambda. And if you then take linear combination of those, the Rayleigh quotient is still lambda. And then the variational characterization of eigenvalues tells you that the Laplacian has at least so and so many eigenvalues below lambda, where you have the dimension of the eigens of this space as a lower bound. So that's something which was observed by Courant. And now I need another blackboard.
And your workbook's in any dimension, right? So it's not surfaces.
Yeah, some of it will also, I will later, if I have the time, come back to surfaces. But yeah, some of it is in higher is for higher dimensions, some of it is for surfaces. So maybe maybe I just so you have so say phi is again lambda eigenfunction. So you have the collection of nodal domains. The nodal domains of phi. Then you have so we are looking at a covering. So if you have such a nodal domain, you can look at the pre-image, and that need not be connected. It has connected components. The connected components of p to the minus 1 of ui. So in general, ji, of course, it has at least one connected component, but it could have many. And then for ij given, you define the following function phi ij on S prime. So it's a function on S prime. Let me just copy so that it's correctly done. So you take p star of phi on uij, and you divide this p factor divided by kij, where on uij, where kij is the degree of p from uij to ui from the subcoloring. And then it's 0 on other uik, and it's p star of phi divided by the degree of p otherwise. So for each such group, you have this kind of this definition, and it's done in such a way, such that that's the little exercise. If the Rayleigh quotient of phi ij is equal to the Rayleigh quotient of phi, the phi ij are all they are linear. So the dimension of the space linear.
Can you push down the blackboard a little bit so that we can read the top line?
Yeah. It's a little higher.
Yeah. Mm-hmm.
Sure. What can be seen now? Yeah.
Okay.
So you take the linear hull of these. And then the dimension of x, that's also an exercise. The dimension of x is equal to the summation of the ji of the ji, they occur here, the index family for the pre-image, minus I plus 1. And then you intersect x with p star of the functions on M. That actually consists only of R phi p. That's the functions which you don't really use to produce something new. That's the old ones. But the new ones, so these are new ones. If you have the new ones will be of dimension summation of ji minus I. And this one goes away from here, yeah. So we get many new eigenvalues if we have non-connected pre-images. And this is just an exercise to work it out. It's not really a big thing once you know it. So the conclusion, let me write down the conclusion for the eigenvalues, including multiplicities, of course, as always. So we get as conclusion. So I denote the function which counts eigenvalue including multiplicity by n, the function of n. We take all eigenvalues below lambda, and we do this for m prime. And I split this I into ones, for each I a one. These numbers are all greater or equal to 0. So you see, if you have one I where this Jij is bigger than 1, you get new eigenvalues, and you get many more eigenvalues if you have many open subsets to play with. So that's a necessary condition. That's a sufficient condition for getting new eigenvalues. And it also shows something if you compare it with the result, which I maybe. Oh, it's gone. So the result of height and McGee, which have this, which say that asymptotically almost surely you don't have new eigenvalues. It means, for example, this, for example, implies that all eigenfunctions for all eigenvalues below 1/4 minus epsilon, if you pull them back to these covering surfaces, the nodal domains all stay connected, which is, I think, an extremely strong condition. So it's a topological condition which comes out of this observation.
So this says something about the fundamental groups of the nodal domains, right?
I guess, yeah. I actually don't really. I mean, there are easy constructions where you get non-connected ones also, yeah, as must have happened in this simple proof. But I can also construct So for the case which we discussed, which for this height McGee result, you have a free group as fundamental group for the whole surface. What I wanted, and so you have many. So what I wanted to say is you have many coverings of degree n, because what they are kind of parameterized by representations of the symmetric group in the set 1 up to n. And so if n grows and grows, so it is by the symmetric group generated, I mean, the symmetric group in the number of elements of the generating set of the free group. And so when n grows, you have these representations in the set from 1 to n, and there are many more, there are many representations. But what is also easy to see is the following, that for any such covering, so we suppose we have such a covering and it is stable, nothing new occurred. There is a twofold cover where already lambda 1 decreases. So if you have many where you have stability, you also have many where you have instability. But you have to go one step further. Yeah? You have to go from n to 2n. Let me explain how you do that. It's quite easy. Namely, so let phi be a lambda 1 eigenfunction on S. So S is now a Riemannian surface, need not be hyperbolic. Then phi has two nodal domains by Courant. Now in dimension 2, there's the result, there's the regularity theory of Cheng, which says the following: the set of zeros over lambda eigenfunction is a graph where the edges are embedded lines and the vertices look like follows. So they are equiangular and smooth. We have smooth curves passing through the vertex. All have, of course, even degree, because otherwise you couldn't have this equiangular and even degree. The even degree follows easily, by the way. So it is a very nice graph. So you can think of the nodal domains as submanifolds with corners. And so we have two nodal domains. The intersection of the boundaries is a set of zeros, the nodal lines. And so our surface is a union of two subsurfaces. And the first possibility is that they intersect, that the boundaries of these nodal domains consist of one circle. Now I want to do the following assumption: chi of S is less than or equal to 0. Because otherwise we are in the case of the sphere, which we don't, what I say is not true. So what you can conclude from that, if chi of S is less than or equal to 0, is that one of these components contains a curve, a closed, simple closed curve, and a line from the boundary to the boundary, which intersects this closed curve in one point. Then you have these points on the other side, on the boundary, and you connect them to a chosen point X. So what you get from this closed surface is a homomorphism to the integers, namely over to that, or to Z over 2Z if you are in the non-orientable case. Let's take the orientable case and we have Z. So that actually it's a non-trivial homomorphism because there is one curve where you have the value 1. It's a homomorphism from the fundamental group pi1 to that. And if a curve just stays inside this fundamental in this nodal domain, the intersection is 0. And now, if you do the topology correctly, then you see that the number of connected components of this nodal domain in your covering consists of p components. There's actually p components. So you put what is the covering? I didn't say what the covering is. The covering is the one. So you take the intersection. You have an you go to Z, and then you proceed to Z over PZ. Then you have the homomorphism to Z mod PZ. This defines you a normal subgroup of pi1 of n comma x of index P, which gives you an index, which gives you a degree P covering, Riemannian, you make it Riemannian. And the pre-image from the setup, the pre-image of this subset here will consist of the degree of the covering times many components. So we can apply this if P is equal to 2, for example. You can also do this in the non-orientable case. You get a twofold covering. And from this twofold covering, you get that actually the first eigenvalue of S green is smaller than the one of S. So stability in 2n, if you have stability, I mean this phenomenon that Haidt and McGee show. If you have stability in degree n, you get from this you get an example of instability in degree 2n. So there are also many where you have instability, but n versus 2n, you see there must be some exponential growth of number of couplings. Okay, so that's about it. So one can work out this argument and get some more specific numbers and results, but this is kind of the main idea of taking intersections with curves. I hope that is. I didn't work out now the details for how to conclude that actually we have these p components in the pre-image, but that's not difficult.
So this means that these coverings in the result that you cited are really very exotic. So they are not given in any explicit way, or
certainly not explicit. It's what?
Yeah.
Which coverings belong to them or not. I mean, it's just this kind of measure theoretic results which you get from random matrix theory. So there's nothing about how these coverings look like. Yeah. But what we get is whatever you take as such a covering from what you get from this probabilistic approach, there's a twofold covering always coming with it, which is unstable, which is lambda 1 smaller than lambda 1 in the base.
Mm-hmm.
Okay.
Sorry, I missed. Can you repeat the statement because I just came back.
Yeah.
Can you say that? Repeat it? Yeah.
So I write. So there's a more general statement, but what I explained is the following: given so any S surface with a Riemannian metric and etc. Say closed surface, so that we don't have to worry about the essential spectrum. there is a two-fold covering. With lambda 1 of S prime less than lambda 1 of S. So that's what okay. So the closed surface should have chi of S less than or equal to 0. Yeah, so that's a result. I finish by stating some result which is also in higher dimensions, but I don't really have time to explain it.
Yeah, I mean, we started a little late. You can take your time.
Yeah. So I will maybe then use my hands to explain some of it. So given so how should I state this? Let me see how I state it. Oh, okay. So this works. So in the case where M is compact, this is infinity, of course, and that's not a condition. Actually, it's also in general not really a condition. And greater element N0 such that any covering I should be more careful. I will take lambda 0 of M tilde such that any covering, any finite n prime to M of degree n greater or equal to N0 has lambda L of M prime. So that's including multiplicity, counting eigenvalues below the essential spectrum. The essential spectrum, this number and the corresponding number of M prime coincide because the covering is finite. So what I'm saying here is above the essential spectrum of the universal covering, you cannot expect any kind of stability, any kind of result which we had, like Heidelberg may be below 1/4 minus epsilon.
Werner, in your first example, you allow Klein bottle? It's Klein bottle is okay in your first statement.
Which statement?
In the previous, a surface is a characteristic non-positive. What about Klein bottle? I worried about Klein bottle, certainly.
The Klein bottle?
Yeah.
So it's about the two-fold cover.
Right, exactly. There are not too many.
Yeah, so Klein bottle has a two-fold covering.
But not only one, yeah, essentially. Yeah.
I'm not sure. I'm not saying any two-fold covering exists. A two-fold covering. It's actually not so clear what kind of. So let me just repeat how we got at it.
No, Klein bottle has unique double covering.
It has a double covering.
Only one, right?
This I doubt.
Maybe two, yeah.
Maybe more, yeah. Let me just tell you how I get it. And then, so what I'm saying is you take a lambda 1 eigenfunction on your Klein bottle. It separates the surface in two nodal domains. the common boundary is either
I see.
either a circle or a number of circles. And here I draw the picture. If you have one circle, then in one of the pieces, you find a closed curve together with another curve which goes from the boundary to the boundary, which intersect once.
Okay, I see the idea. Okay.
You continue and make it a closed curve. And then this intersection with that closed curve gives you a homomorphism from by 1 of m comma x to z. You take the pre-image of 2z, that gives you a twofold covering.
Okay, I got the idea, yeah.
Yeah, the pre-image of this nodal domain is not connected under this. That's the main point. So then you get more, you get additional. So actually, I mean, I just indicate the idea. So the idea is very simple of this new statement now. Yeah. So given a number which is above the bottom of the spectrum of the universal covering, like over 1 over 4 if you are in the hyperbolic surface case, and the number L in n, then you find sort of an a priori lower bound on the covering. If you are above that lower bound, you have at least L eigenvalues below that lambda. So you cannot have stability in the sense of height and maybe in any kind of way. Yeah? And the point is the following. So because your lambda is bigger than lambda 0 of m tilde, you find a function phi tilde on m tilde with compact support, such that the Rayleigh quotient less than lambda. And this, so it's inside some ball of radius r, where you have this support. And so this is a ball of radius r about some point x tilde. So we have that on m tilde. So then we observe the following. If the degree of the covering is sufficiently high, then, so we have x tilde, we have x and m, also the ball of radius r, but of course it is not evenly covered necessarily. It's just a big ball maybe. It's not necessarily small. Yeah? It will be big in general if you get closer and closer to the essential spectrum, to lambda 0. Then you have, if you have, so in between, if you have a covering, you have the pre-image of this point in the covering. What I'm saying is, if the covering has sufficiently high degree, then you find at least L such points so that the corresponding balls of radius r are disjoint. Okay, that's easy enough. Hopefully you can believe that. That's just simply, you take maximal subset and you find it. It must be bigger than L if you're covering sufficiently high. So what do you do now? So you have this point or an image of this point under the fundamental group maps onto this ball of radius r about that point. So either this x or some other x from the fundamental group, which you get from the fundamental, you get the ball of radius r. You push that function also with the fundamental group around all the balls from of the orbit. And what you then do is on these balls, you cannot take the original function phi tilde, because it's not evenly covered, this ball. But what you can do is the following. You look at the following function. You take phi tilde, you take phi of x is equal to, you take phi of x squared let me. Okay, so no, not too many x's. You take any point y, and then you have a once in the pre-image of this ball, which maps onto this ball. You take the points y and p the minus 1 of x intersection er of x, and you take the square root of that. So you take all times. So you take this function. If this function phi, if it is Lipschitz, this other function is also Lipschitz, and the norm of the gradient you can estimate also. It's also yeah. So what you do with the Rayleigh quotient is you estimate that the Rayleigh quotient of this function phi is at most the Rayleigh quotient of phi tilde. So from this you get a function with support on this ball, which has Rayleigh quotient also estimated by lambda. And you have L such at least L such disjoint balls. You have then L2 orthogonal functions with that Rayleigh quotient. So then you have this result. Yeah. I think that is in short the proof of that result. It's very elementary, of course, again. Okay, so yeah, that's it.
Yeah, okay. Thank you, Werner, very much for this beautiful talk. Are there any questions or remarks?
I'm not a specialist.
Yeah.
So, what I haven't gathered from your collection whether this stability is a topological property or not. So, for example, if I fix the cover and start varying, say, for Riemann surfaces, and start varying the Riemann surface within its modular space.
Yeah.
How the stability pattern, is it changing or is it kind of not changing?
I'm not really an expert of that proof. I suppose that it's not known, because I mean you construct more or less by hand for each Riemann metric. You construct by hand something close to a resolved. So up to compact the perturbation, you have the resolvent. And this construction by hand, of course, you can do this in smooth dependence on the Riemannian metric, on the hyperbolic metric. But then at some point you involve this kind of probability theory. And there are the matrices which you consider, so random matrices, you have matrices. The matrices are not the same, but maybe probably they are still close to each other. But I actually don't know this. Maybe that the random matrix theory tells you something about what you get if you have matrices which are close to each other. But I don't know that. It could be, but I'm not sure whether that's known. So I actually didn't study anything in random matrix theory, so I'm not familiar with.
But in your arguments, you can also vary.
Yeah. These arguments, it's rather stable.
It's topological.
Yeah. It's purely topological. I mean, the geometric constructions are kind of trivial.
Is there any way for a given covering understand using this topological approach whether it is stable or not, for example, for the first eigenvalue?
Yeah, so we don't have sufficient conditions. We have just necessary conditions. The necessary condition is the connectedness of the pre-images of the nodal domains. You should not have more for all of these eigenfunctions. So the nodal domains, that's kind of strong, but it is not. It is probably not. I don't think it is sufficient.
And this construction depends on the choice of a particular eigenfunction. Yes. So if your if your eigenspace for lambda one is of high dimension, you can pick different.
Then
for one of them, you can obtain one picture, and for another, you can obtain it.
So you get you get certainly some sort of discontinuities here also if you look at things.
So I've got a question. Is there any kind of, say, parallel discussion for Dirac spectra? Or is this, or maybe the question doesn't make sense, I don't know. So you look at always at the Laplace spectrum.
So what is important, and so this is kind of topological approach, And so what is essential in our approach is so Will and McGee, it's I'm not sure Will and McGee, but I have to think about it. But for our approach, we need nodal domains in that. So if you have Dirac, you have higher dimensional vector bundles, and so of course you could at the norm of these eigensections and so on. But I'm not sure whether.
Okay, so it's not obvious.
Maybe there is something, but I really don't know.
Yeah. Okay, any more questions?
Yeah, I also have a question. Werner, unfortunately, I missed the last few minutes of your talk, so maybe you said this already, but is it correct that the only information that you have about nodal domains is that for a compact one, it's 2?
What?
The number.
What is the information of, so you said that you can interpret this other result as saying something about the topology of nodal domains. So
first of all, for lambda one eigenfunctions on the surface, you have exactly 2 nodal domains. Also for other remaining manifolds, it's not more than 2 domains.
Yeah. So that was the question. So that's the only thing that you.
But this construction, if you compose it with a projection onto Z mod 2Z, you get and you take the kernel of that as a subgroup here, you get a covering, a twofold covering. And what I said is that the pre-image of this nodal domain consists of 2 components.
Yes. Yeah.
And that's simple enough, but this is the main observation in this example. If you have more than one boundary curve, you can also do this differently. You just walk from one circle to the other and close it up, and then take the intersection with one of the boundary circles.
I think this I understood. I was just so. And the other thing you mentioned is that there's a regularity result that tells you that the boundary is basically
So that's a regularity result of somebody called chain. And for surface, it says the nodal line, the nodal set consists of is for if you have say a compact closed surface, is a graph, smooth graph. Actually, in the vertices, it's not completely smooth, but the edges are smooth. And in the vertices, you have even degree, and the edges meet equivalent. The angles are all the same.
Yeah. So where does this come from? Does this minimize something, or where do these equal angles?
I think that's because you can choose coordinates that it comes close to Z to the n for some n. Yeah. Okay. And then you get something like the curves. These curves through the vertex. I think in this point they are only C1. Maybe I'm not sure. I've forgotten that. But anyway, it's very very nice graph, so that you can do topology easily.
Yeah, and in higher dimensions, there's nothing. Yeah,
really. I mean, there's something in that paper which is in higher dimensions, but I think it is not. There's some gaps there, but in higher dimensions, what you expect, maybe I'm not sure whether there are contexts under something like polynomials. You have zero set of real polynomials, of some specific polynomials, like harmonic polynomials or whatever. Yeah, but I've forgotten that. In higher dimensions, it's not that easy. No, it's not known actually. There are some results, but it's not too well known what it is.
Okay. Yeah, thank you.